Well, I hope you guys are all underway in completing the problem sets. And here are some 4 questions, and these 4 questions are mainly about strong bases and strong acids. Just as a reminder of the calculation bit that we already took. And what are the strong acids, guys? Let's discuss strong acids first. What are the strong acids? Strong acids are HCl, HBr, HI, so the halides, except not HF, nitric acid, sulfuric acid, the first dissociation of it, this is a diprotic, and perchloric acid, which is a bit hard to know, but these are the only 6 strong acids. So these will dissociate completely, and when they dissociate completely, we mean that whatever strong acid I have in solution of water or reacting with water according to Bronsted, this becomes A minus and H3O plus. And so the concentration of this acid in solution, and I sometimes say initial, it means that before dissociation, whatever the concentration is before dissociation. It could have been a diluted one or whatever, but this is before dissociation initially. We have nothing in solution, and then at the end we will have 0 HA, nothing is left over, all of the HA is converted to A minus and H3O plus. And so here is a conservation, if you will, of the mass. So all of the HA is converted to these 2 species, and thus my pH is governed by the H3O plus. So pH is minus log of H3O plus, which is minus log of C, since the H3O plus is C. Now, guys, this is all I need. I don't need to do autoionization of water, conservation of mass, Kw, in order to get what is the pH of a strong acid. Okay? That's all I need. That is all I need because this is my governing equation. It's the HA dissociating into A minus and H3O plus. But when is this the governing equation? When is this equation determining the concentration of H3O plus in solution? This equation takes over, let's say, the other equation, which is water autoionization of water, when the concentration of the acid is greater than 3.2 times 10 to the minus 7. And if you take the log of this, or when the pH is greater than, less than, when my pH is less than 6.5 or equal to, because the minus log of this is minus log of C, and minus log of C is my pH. So when my pH is less than 6.5, then only HA contributes to the H3O plus in solution. So here in this side, I will only have HA. And the idea is if this pH is actually bigger than that, bigger than 6.5, this area after the 6.5 is when I start to require water contributing. In the area between 6.5 and 8, not only water contributes to H3O plus, but also HA contributes to H3O plus. So I have 2 equations running at the same time. And when my concentration of my acid is less than 10 to the minus 8, then only water contributes to the H3O plus, and actually HA is negligible in the solution. Actually, that's the net, and that's all you really need to know. Now, however, who said 6.5 is the pH of the cutoff? Who said 8 is the pH of the cutoff? Who set this number? What gives off these numbers? Who decides that it's 3.2 times 10 to the minus 7, that the concentration, I can neglect water attribution to H3O plus at this concentration? Who said this? That's when I need validity conditions and to know where did this number come from. But to solve problems, you don't need to know where this number comes from. And to get a pH value, you don't need to know where this number comes from. Okay? And I don't need different calculations to get this pH. Okay? So all pHs, we don't need that. But I will discuss, of course, where these numbers come from after we solve, because it gives you a better idea of how to do calculations with solving. With bases, it's the same idea as with acids and the same cutoff point. And so we're just going to go ahead and solve number 24, 25, 23, and 31. And number 24 is a strong base, but they give you a mass. Number 25 is a strong base, but they do a dilution to it. Number 23 is a very dilute acid where its concentration is less than 10 to the minus 8. And number 31 is a very dilute base where the concentration is also less than minus 8. Right on. Number 24. So with number 24, you can do the reading, of course. This is a base which has a mass of 0.12 grams of sodium hydroxide, where I put it in 500 milliliter beaker of water, or I add to it 500 mils of water and 0.12 grams dissolved. Okay, so what do you need? They didn't give you concentration. Of course, you need to calculate the concentration, so go right ahead. And you already know that NaOH is a strong base and dissociates completely. How do I calculate concentration? Concentration is the number of moles divided by the total volume in the solution. And you know that the number of moles is the mass divided by the molar mass. And it's not the molar mass of OH minus, guys. It's the molar mass of NaOH. And watch out for that. A lot of you make the mistake. Now, if you're lucky, I give you the molar mass of the salt, the sodium hydroxide, which is a salt actually. It exists as a solid, but then it dissolves, and it's a strong base. This sodium hydroxide, you have to calculate him from the molar mass of each of the elements, sodium, oxygen, and hydrogen, which you all know how to do. Then you have the mass in grams divided by molar mass. That gives you moles. And then you have to divide by the volume in liters. And do watch out, okay? Because this we make, if you leave it in milliliters, you get a completely different answer. And you have to here convert the volume, okay? It has to be in liters. And so my new concentration, or actually my concentration is for NaOH, 0.06 or 0.006. You right away ask yourself, is this number big enough? In other words, is this number greater than 3.2 times 10 to the minus 7? Yes, it is. And if it is, that means only this base contributes to the pH of the medium. And if only this base contributes to the pH, then simply I calculate the pOH, which is minus log of OH, and then I can get the pH value. Or you could, if you really want to go for speed, you would know this one. pH is simply 14 plus log of C, where C is the concentration of the base. Because, again, with base, just like acids, if C was my original concentration of OH minus, I had nothing here. After, the OH minus will become 0, and all of it will be converted to my sodium, which is a spectator, and my OH minus. And thus, when you do the calculation further, you get pH is 11.77, and the answer is D. Number 25. Number 25 is also a base, and calculation. And so here we have a strong base, also potassium hydroxide. Again, what are the strong bases? Just a reminder, it's row 1, the alkali earth metal hydroxides. So we have sodium hydroxide, lithium hydroxide, potassium hydroxide, rubidium hydroxide. We also have the calcium hydroxide, row 2. Sorry, not row, column. Column 1 and column 2, okay? Column 1 and column 2 of the periodic table. Anywho, so the concentration is 0.05 originally, and now they asked you, they said that the reaction was diluted, or the reagent was diluted. How did they do the dilution? They took 10 milliliters and placed it in a 500 milliliter volumetric flask. That's what they mean by volumetric flask. And watch out for this, guys. So if I have my original solution, I'm going to take from the original solution 10 mils and put it in a volumetric flask, which has a mark that you fill the water to the mark, and once it's filled, this is a total volume of 500 milliliters, okay? Total volume. And one of the mistakes that you guys tend to do is you add the 10 to the 500, and this is wrong because later on in titrations we do that, but watch out. For dilutions, we don't do that. The total volume is 500 milliliters. Of course, this is an MCQ question, and they ask you, what's the pH and what's the concentration of OH minus, H plus, and so on. First thing you have to do, of course, is calculate your new concentration, not the diluted. So you use CV equals C prime V prime, and you find C prime, which is your new concentration. And again, that's the concentration before dissociation of the KOH. So the concentration of KOH in solution will be the old concentration times the volume used from that divided by the total volume of the solution, or the new solution volume. Of course, the volumes, you don't really need to put them in liters, and they're put here in liters, but it's not necessary. You can keep them in milliliters, and once they're in milliliters, you are fine. You have a new concentration of NaOH, and of course, you all know how to do that. Once you have your new concentration of KOH, then you compare it and you say, is that greater than 3.2 times 10 to the minus 7? Yes, it is. That means that only the KOH dissociation will be effectively determining the pH. And so the pH, like I said, we can use this fast way, is simply the pKW, which is 14, plus log of the concentration of the base. Okay, and I don't do that. And so you go back to the answers and you will see that the answer is A, C, and E. And make sure so that's the pH, because the pH is 11, that's one of the answers. The concentration of OH minus is 1 times 10 to the minus 3, and I can use this equation, that's a third answer. And now it's actually a little bit of a new theory, and that is, here's a strong acid, HCl. And they gave you the concentration 10 to the minus 8. And yes, guys, at first sight, you may think, oh yes, that's great. Let me just do pH equals minus log of the HCl concentration. And if you do that, what do you get? You would get that the pH is what? If you had done minus log of this concentration, you get the pH. And if you did that, you get a pH of 8. And the first thing that has to stick to mind is, wait a minute, pH 8 is greater than 6.5. Okay? pH of A is greater than 6.5. And therefore, I have to look at the autoionization of water. Or, in other words, look at this number. This is too small. This is very, very dilute. And when the concentration of the acid is very dilute, or a little bit dilute, less than 3.2 times 10 to the minus 7, then, again, this is only acid, is in this side that I can neglect water. But in all other cases, I have to consider water. And in the case when the concentration is equal to or less than 10 to the minus 8, well, that's actually when only water contributes to the pH of the solution, and actually HA is negligible in the solution. Okay, so I can remove HA and it's no longer going to affect my pH. And what is the pH of water? You all know that the pH of pure water is 7. And that's the number. So the answer is 7. Now, actually, the answer sometimes is like 6.99 or 98 because it's going to be slightly acidic if you actually consider the amount of HCl coming in. But we say the answer is simply 7. Okay. For base. For the base, this is a base with a concentration less than 10 to the minus 8. This is KOH, and they gave you KOH with a concentration 10 to the minus 10. And they want the pH value, okay? So if some of you decided, oh, okay, the pH of this is a strong acid, great. The pH is, I memorized this, 14 minus log of the C, plus log of the C, watch out for this, plus log C. And when you do that, log of C, log of 10 to the minus 10 is 10. Log of 10 to the minus 10 is 10. And 10 plus 14 is 2 odd, so that's a bit weird. Okay, so there's something wrong here. Delete. Anywho, that's okay. So the first thing you said, okay, this concentration is clearly less than 3.2 times 10 to the minus 7. And if this concentration is less than this, then we have to actually start to consider autoionization of water. And this concentration is 10 to the minus 10. It's way beyond the limit of C less than 10 to the minus 8. It's actually lower than that. And that way you know that the base, you have to simply take the only water into consideration here, because the base concentration is so bloody low that it's essentially negligible to the contribution of pH. And so the pH is not going to be 10, or a pOH is not going to be 10, or the pH is not going to be 7. The pH is actually not going to be 4. The pH will be 7, okay? And it's actually a little tiny bit greater than 7, so they have an answer here between 7 and 8. And so, yeah, you have to watch out for these concentrations. Now, there's one more area which we really didn't look at only, and that is this quadratic equation. And frankly, this is when the concentration of the acid or the base, the strong acid or the base, is between 3.2 times 10 to the minus 7 and 10 to the minus 8. Okay, so if that concentration is between these two numbers, so it's actually bigger than 10 to the minus 8, but it's less than 3.2 times 10 to the minus 7, then you have to use this quadratic. And we're going to derive this quadratic equation in two different ways. There's an easy way, there's a harder way. I like the easy way, the way you think about it, but in the end, honestly, do memorize it, okay? You have to, this is the only quadratic that I'm going to tell you memorize it. Great. And next time we're going to get into a recording on the validity and where did these numbers come from. Why did we choose 3.2, not 3.3? Why is it not 3.4? Why is it that the concentration is less than 10 to the minus 8? Why is it that we didn't do it 10 to the minus 9, the cutoff? So where did these numbers actually come from? Okay, and that's when we have to consider, you know, quite a bit more detail on theoretical yields, but theoretical calculations. Otherwise, you should still know how to solve these sets of problems. Okay, till next time, see you.